audience. Can you hear me? Okay, so thank you, Shankar, for the kind introduction. And I wanted to acknowledge all the other institutions, but you did it in such a good way. I can never do it as well as you. So thank you, all the other institutions. So today I'll give you a talk about seawater desalination. And it will be more a big and overview type talk with some technical details, of course. And then hopefully I'll provide you with some information to answer the question, is seawater desalination a sustainable solution for global water scarcity? And in the end, I will tell you what's my opinion. But again, it's more open-ended. You can decide by yourself based on this information. So first, I would like to tell you where I came from. I'm from the environmental engineering program at Yale University. It's part of the chemical and environmental engineering department. And probably you can see here some faces that you recognize. Sorry for the resolution. I think part of the screen here. But I hope you can see it well. So we also have affiliated faculty, mostly from the School of Forestry and Environmental Studies that you see here. Some of them are well known, like Tom Gradle. And we cover all aspects of environmental engineering, from water, air, and soil, and also cover chemistry, biology, and physics of environmental engineering. So before I start my talk, I would like really to thank the people who did all the work. This will be a presentation based on my work in the last 10 years. I'll try to summarize it. But really, the people who do all the work are the graduate students and postdoc, and I really would like to thank them. This is sort of like roughly my current group, at least in the last few years. And I would like to give a quote from the Talmud and about learning. So I've learned a lot from my teachers, which is true. I had a great advisor. I've learned more from my colleagues. But really, I learned the most from my students and postdocs. So whenever I say students, it means students and postdoc. And I'm glad to see many of them are here that came from other institutions. So really, I would like to thank all the students. They did all the work. So I would like now to start with the technical part. And I will start with a slide that showed the top 10 global challenges. And I will have a quote here. This is the list from Smalley, it was at Rice University. And it's not surprising that you see that the top global challenges, you see energy and water on the top of the list. And indeed, many of the challenges that you see there are somehow related to water and energy. Specifically, we can tie together the water and energy in what we call the water-energy nexus, because they are very, very related. You will see it during my talk. To get water through desalination, you will need a lot of energy. And to get power and energy, you also need a lot of water. So they're really interrelated. We can even extend this nexus to the water-energy-food nexus. And again, it's an area now of active research. NSF has a call for proposals in this area. And part of the reason why we extend it, because you will see, again, I'll show you some examples later, that food and agriculture consume most of the water. Most of the water that you consume really doesn't come just from drinking or a few things that you do on a daily basis, taking a shower. It's really food and agriculture. So indeed, the new United Nations Sustainable Development Goals include a lot of challenges that related to water and energy, as you can see here. You can see zero hunger, again, related to food. Number 6 there is clean water and sanitation. Number 7, clean energy. And of course, climate action, which somehow related to energy. So these are the new Sustainable Development Goals that we need to meet by the year 2030. Now, as I told you, there is a huge, large increase in the consumption of water, and mainly because of population growth. And you can see it here. These are the increase in global water use based on sector. As I told you earlier, agriculture consumes most of the water. And of course, we have water from industrial and domestic water. So I don't need to convince you, most of you are here from environmental engineering, that really there is a big problem that we do not have enough water. Indeed, I will show you how much water we eat. Again, water, we think about drinking, but we actually eat water because there is a concept of virtual water. Everything that you eat, if you have an apple, to produce this apple, you need 70 liters of water. Some of you ate hamburger today, probably not. One hamburger will consume 2,400 liters of water to produce this piece of hamburger. If you think that you will go and eat some healthy food, they also consume a lot of water. One head of broccoli consumes close to 5 gallons of water, and so on. Now, I don't know how many of you follow the drought, news about the drought in California. And do you remember who was the evil of all in the drought in California? Almond. You know, the almond growers were really under a lot of troubles because one almond, just one almond, consumed 1.1 gallons of water. Just tell you that agriculture really and food consume a lot of water in many ways. So the question is, how do we increase available water supply? We can get a certain amount of water from the hydrological cycle, but it's not enough. So we need to find some other ways to increase the water supply beyond what we can get from the hydrological cycle. And this is where we use engineering. We can use engineering to either desalinate brackish water and seawater, or to reuse municipal wastewaters. So my talk will focus on desalination of seawater. And when we discuss desalination of seawater, it is critical to enhance the sustainability of desalination. So I will talk on many aspects related to the sustainability of desalination, mostly the energy use and the environmental impact. So let's start with seawater desalination, and let's talk about the features of seawater desalination. First, it's offer an unlimited steady supplies of high quality water because the ocean is vast. You can take as much water, believe me, you will not lower the level of the sea. Indeed, maybe it be a good idea to lower the level of the sea. Also, you can produce fresh water without impairing freshwater ecosystem because when we take water from groundwater, reservoirs, and lakes, we affect the ecosystem. We need a lot of water to have a healthy ecosystem. So these are some of the two good features of desalination. However, there is always good and bad. And some of the bad things about desalination, it's more energy intensive. It takes up to at least 5 times more energy to desalinate seawater compared to, for example, treating water just from a reservoir with relatively clean water. And also, there are a lot of concerns about the potential environmental impacts, especially of large-scale desalination plants, and I will show you some examples. So we will focus a lot on these last two, the energy and the environmental impact in this talk. Now, let's talk about seawater desalination. The state-of-the-art technology for seawater desalination is reverse osmosis technology. It's membrane-based. This is a typical desalination plant, reverse osmosis desalination plant. There is an intake structure that you take the water from the ocean. There is pretreatment, similar to what you have in pretreatment, treatment of drinking water. Then it goes to the heart of the process, the reverse osmosis stage, that really does the desalination, removing the salt from the water. And then there is some post-treatment, and once we have the brine, I don't know if you can see it, you can discharge the brine to the ocean. And the lines that you see here, the thickness of the line tells you roughly about qualitatively the energy consumption. Most of the energy will come for the reverse osmosis stage. So my focus, in this talk will be really mostly on the reverse osmosis stage. As I told you, there are numerous seawater reverse osmosis desalination plants that were built all around the world. Just last year, or this year, we completed the largest seawater desalination plant in California, in Carlsbad, 70 million cubic meter per year. And it took 12 years of discussions, fights with environmentalists, etc., to build it, just to give you an order of magnitude how long it took. There are other countries. Israel, for example, completed 5 huge desalination plants. These are just the 2 recent ones, and each one of them is twice as much the capacity of the one in Carlsbad. For example, the one in Sorek was designed for over 200 million cubic meter per year, and it operates now at about 150 cubic meter per year. And another one in Hadera in Israel, and there are 5 of them. Total capacity of close to 700 million cubic meter per year. It's huge. So in this talk, to answer the question if seawater desalination is sustainable, I would like to address 4 major questions. The first one would be, what is the current energy efficiency of desalination? I will give you all the limits, how much we can do the best, and what's the current energy consumption. Then I will address a very important question, can novel materials reduce the energy of desalination? There is a lot of research on efforts to reduce the energy of desalination, and many scientists, especially material scientists, jumped into materials as the way to really reduce energy. then I will go to process engineering. Are there any innovative system and technologies that can reduce the energy of desalination? And then end up with the question, what are the environmental impacts of desalination? And hopefully by presenting all this data, we will be able at least to decide if seawater desalination is sustainable or not. Again, sustainability is very difficult sometimes to quantify. So let's start with the first question. What is the current energy efficiency of desalination? And I would like now to show you what we call the thermodynamic limit of desalination. This is the energy that you will need to desalinate, and you will never be able to do it with less energy than this, because thermodynamics dictate, if you assume a reversible thermodynamic process, that you will never be able to desalinate with less energy than the value that I'm going to show you here. And this is regardless of the technology. It's not only for reverse osmosis, any kind of technology. So when you do this calculation for zero recovery, if you check just one drop of water, fresh water from the ocean, it's 0.76 kilowatt hour per cubic meter. 1 cubic meter is 1 metric ton or 1,000 liters of water. And if you do 50% recovery, what we do in seawater desalination nowadays, you have the seawater, you produce half of it as clean water, and half become as a concentrated brine. And for this one, you need 1.06 kilowatt hour per cubic meter. So you will never be able to do better than here. And any I get sometimes some calls or some students from Yale, I have an idea and I can desalinate something with 0.1 kilowatt hour per cubic meter. You can't do because you will violate thermodynamics. And no one was able to violate thermodynamics in the last millions of years. So now let's go specific details about desalination, the energy of desalination. When you desalinate seawater or anything, you have the membrane are in a membrane module that have a lot of area, and you put 6 of them, 7 sometimes in series. It's about 6 meters long. And you can think that the seawater comes here, and as it goes, you extract clean water, so the water that's remain here, the brine, become concentrated as we move. So we can think, we started the entrance, you can think about the osmotic pressure of the seawater, and as you go and extract clean water, the osmotic pressure increases until you reach the exit here. So this describes the curve of the osmotic pressure, and the minimum energy of desalination that you can calculate based on thermodynamics, just the Gibbs free energy of separation, is equivalent to the area under the curve, and this is the expression that you can get if you follow the mathematics. Now, the way we operate reverse osmosis, we need to apply a pressure that equal at least the osmotic pressure of the exit brine. Otherwise, we will not get water coming through you need always a pressure more than the osmotic pressure. So again, this is the minimum energy, and these are the irreversible energy losses. And remember the value, the area under the curve for 50% recovery is 1.06 kilowatt hour per cubic meter. The way desalination plants operating, I told you need to apply pressure which equal at least the osmotic pressure of the exit brine. So we can define now a practical minimum energy. Because we need to apply such a pressure, if we know this pressure and we know just the, per cubic meter, we can just translate the pressure to energy by converting the units. And the practical energy is 1.56 kilowatt hour per cubic meter. It's more than the reversible thermodynamic process, because if you recall thermodynamic, a reversible thermodynamic process is infinite inside with just drops of water coming. So this is just the practical, you need to have some driving force that drive the water. Now let's see what's the energy consumption of reverse osmosis stages since the invention of the reverse osmosis technology in the late 60s. This describes the energy consumption kilowatt hour per cubic meter just for the reverse osmosis stage. Since the invention of reverse osmosis, I don't have any data here, but I can tell you it doesn't change. It stays the same. We see a dramatic improvement in the energy consumption, mostly through the improvement in the permeability of membranes, introduction of pressure exchangers that can recover the pressure in the brine rather than discharging it with all the pressure, and many more efficient systems and pumps. Now, I can tell you that these are the improvements, but in the last 10 years, the energy consumption of desalination of the reverse osmosis did not change. It stayed the same in the past 10 years. You can see it. I can zoom on this part here, and I can tell you They are not much data, but even if you take the data, you cannot do it less than about 2 kilowatt-hour per cubic meter. So just to put everything in perspective, the 1.06 is the minimum energy for a reversible thermodynamic process, which is not practical. It will be infinite in size. The practical minimum is 1.56, and the current reverse osmosis plants, the best of them, consume roughly about 2, maybe 2.1 kilowatt-hour per cubic meter. So if we operate reverse osmosis the way we operate now with fixed pressure, as I showed you, there is some room to improve from 2 to reduce to 1.56, but not below it. So just to give you an idea, the rooms of how much energy you can improve. You cannot make dramatic changes in the energy consumption. Okay, so now this was just the reverse osmosis stage, but seawater desalination plant has many components, as I showed you earlier. Pre-treatment, intake, post-treatment, and the entire plant nowadays, including the recently built, consume between 3 and 4 kilowatt-hour per cubic meter. Most of the plant are about 3 kilowatt-hour per cubic meter, which is 1 kilowatt-hour more than the reverse osmosis stage. But some plants that need to remove boron and reduce the chloride level for agriculture, like the one in Israel, they need to go through many other reverse osmosis passes because boron is in the form of boric acid and is not removed effectively. And these extra passes also add, so for example, the state-of-the-art plant in Israel consumes 4 kilowatt-hour per cubic meter. So remember it when we talk about the future membranes and where we should go. We will refer to this slide again. Okay, so this one I told you the landscape where the energy, how much you can improve. And as you see, you cannot make dramatic changes of energy of desalination because thermodynamics dictate what you can get. So now let's go to novel materials. A lot of scientists, and again, academia, we want to write papers, materials, and so on, and they jump into desalination. And so scientists jump to this area of high permeability, high flux membrane, and they promised, at least the papers and proposals that they wrote, that there will be a quantum leap in desalination. Really, it can have dramatically change the energy landscape in desalination. And the rationale for them was very simple. Again, soon you'll see that desalination is not as simple, but they thought if you have higher permeability membrane, we know from Darcy's law, if we study that if you have less resistance, you need less pressure. And they thought if you have membrane with higher permeability, which means less resistant, you will need less pressure, and you can desalinate with less energy. So this was the rationale. And there were research, and again, published in top journals. Again, whenever you talk about technology, by the way, if you publish it in a very, very top journal, Nature and Science, there is inverse correlation to the practicality of it. So this is an example. They talk about carbon nanotubes. And carbon nanotube, they found that because of the atomically smooth and hydrophobic, that water can go more like a file of molecules. Remember, in fluid mechanics, we learned the no-slip boundary condition. It doesn't hold here. They just slide. And very high flux, and say, oh, we can use it for desalination. Aquaporin, these are the protein channels that transport water in cells of plants and living organisms. And they suggest that if you put this aquaporin, it can transport water at a high rate. You will have a high flux and you will save energy. And also when you have graphene, these are atom thick, carbon. And because it's very thin, just atom thick, if you punch the right holes, it will have such a low resistance that you can really desalinate, what they claim, with almost no pressure. And when you have these kind of things, usually the scientists, some of them are careful, do not promise a lot, but the news media always extend it. I don't know how many of you have seen John Oliver, the Late Week Tonight Show, and he talks once about how scientific studies, how the media turns scientific studies into morning show gossip. He talks about if you eat too much chocolate and coffee and all these things, and it was a very foul language. If you look at this, if you know John Oliver. So something like this happened in desalination. This is Lockheed Martin, which is a very respected company. Again, we fly with their airplanes. They should know thermodynamics and everything. They promised, and they did just model simulation. In this area, you didn't even do experiment, just molecular simulation of atom-thick graphene with some holes, and they said there will be a huge water flux. And I don't know what they wrote there. Maybe they wrote the flux will be 100 times more, and the media turn out and say you can save 99% energy. Again, I showed you the thermodynamic limit. If you need 99% energy, it means to be almost no energy. So we need to be careful when you come to science and so on. However, as I showed you, energy is not governed by the resistance of the membrane. It's governed by the osmotic pressure. The osmotic pressure, it's more thermodynamic controlling, because I already told you, you need to apply at least a pressure equivalent to the osmotic pressure of the brine. And the 1.56 kilowatt hour per cubic meter is, if you take seawater, the osmotic pressure is 27 bar. If you have 50% recovery, the brine will be 54 bar. And if you just do the calculation, 54 bar converted to energy, it will be 1.56 kilowatt hour per cubic meter. So whatever you put, the super high permeability membrane, you cannot desalinate with less than 1.56. And in reality, we apply 10 to 20% more because there is some pressure drop as the water flow in the channel, concentration polarization, and many effects. And the current membrane that we are using already operate at this range. The current membranes are thin film composite polyamide. They have the right permeability to work in this range. So indeed, I can show you now some rigorous numerical calculation that we have done of modeling the entire module in a reverse osmosis stage with all the things. And let's look just in this curve here to show you the energy of desalination as a function of the water permeability coefficient of the membrane. The current water permeability coefficient of the TFC, thin film composite membrane, is between 2 and 3. So you see that the energy of desalination, if you improve from 2 to 3, it doesn't change much. And even if you have it 10 times, it doesn't change a lot. I told you earlier that since 1970, we got a big drop in the energy consumption because the first generation membrane where the permeability very low, cellulose acetate, and this explains why we got this drop. But current membranes will not reduce the energy of desalination. If you have high permeability, you may have less membrane area, but membrane in desalination plant constitute no more than 4% of the total cost. And also, those of you who are in the membrane field, you know that it's impossible to operate at high flux. You get fouling, you get severe concentration polarization. So the answer here really that we do not need high flux membrane to reduce the energy of seawater desalination. Now let's talk about the current membranes. The current membrane are thin film composite polyamide. They are the gold standard in desalination. Since the 1980s, no one was able to find a better formulation than the polyamide. And believe me, the membrane companies work day and night to find a magic membrane, and they can't. It's just good enough. However, this membrane has many features that make it prone to fouling. It is relatively hydrophobic because it's polyamide. It has a rough surface because of the reaction that you make this selective layer create severe roughness. It contains carboxyl group, and also it's very sensitive to chlorine. You cannot just clean it with chlorine or oxidants to kill the biofilm, for example. And all of these make it really, all these properties make it prone to fouling. So my suggestion and arguments that really, if you want to have improvement in seawater desalination, at least on the membrane side, you need to really strive for fouling resistant membrane, because nowadays the way you operate membranes plant, as you get fouling, then the resistance increase and the plant need to increase the pressure so you can get constant water coming out of the plant. And when it increases by 10%, then usually they stop and clean the membrane. So really, I advocate more toward fouling resistance membrane. I will show you just 2 examples from our research group about 2 approaches for fouling. One of them is to prevent organic fouling. And I told you that the membrane is hydrophobic. And organic molecules usually hydrophobic. They like, again, hydrophobic surfaces, and they absorb to the surface. If we can make the membrane hydrophilic, it will reduce the absorption of organic foulants. And I'll show you one technique by Zwitter ionic polymer brush layers. These are polymer brush layers. They have Zwitter ionic monomer that has positive and negative charges, but overall they're neutral. And they have this very strong capacity to absorb water molecules. So when you have the polymer brush, there's this thick layer of water molecules. And for organic foulant matter to come and absorb to the membrane, you need to displace the water molecule, which is energetically not favorable, and it's not possible. So this is why you can create this fouling resistance. These Zwitter ions were used a lot in the biomedical field, but not in the membrane field, at least in the reverse osmosis. So we found some way to immobilize. Again, we use ATRP, it's more like polymerization technique that you need to bind initiator to the membrane, and we use the well-known polydopamine chemistry to glue or attach the initiator to the membrane. This is the monomer. Again, it's bitter ion, of quaternary ammonium and sulfate. And we grow this monomer, and we can control it. ATRP is, you can really control the thickness, I mean, very, very well. And once we grow it, we get this polymer brush layer. And I'll show you some example for these membranes. This is the typical polyamide membrane, hydrophobic, as you see from the contact angle. And once we modify it with the polymer brush layer, we reduce the contact angle to 21 degrees, very hydrophilic. Also, we expose the membrane to a protein which are labeled by green fluorescence. And we soak the membrane in the protein solution. So the control membrane, which was hydrophobic, attached the protein, and you see it by the green fluorescence. This membrane, we did not see any protein stick to it. We also tested it in a reverse osmosis operation, and we saw less fouling and so on. So this is just one example how you can make the membrane more hydrophilic to prevent organic fouling. And we do a lot of other approaches. I'll give you another approach, nanotechnology. I know Texas is very big in nanotechnology. A lot of people do some work here. These are graphene oxide, more like nanosheets here that you see. And they can be antimicrobial. I will not get to the mechanism and so on. It involves physical and chemical interaction. And when we took this graphene oxide, we found a way to bind it to the membrane, taking advantage that the membrane has carboxyl group, and you can find easily the right chemistry to link the graphene oxide. And we found that indeed, when we have this graphene oxide on the membrane, we kill the microorganism and delay to some degree the rate of biofouling. So it's another approach to slow biofouling. Again, I can tell you, you cannot prevent biofouling. Bacteria always win. So as long as you slow it, it's great. Now let's go to the third question. Are there any innovative system and technology that can reduce energy demand? And you'll be surprised now here that when we go to process engineering, we can really have a lot of energy saving. But process engineering, at least for academia, is not attractive. Again, if you have a faculty who want to get tenure, if you write a paper on process engineering, the committee will not look at it favorably. And let's show you some examples. For example, if you have two stages, just instead of operating in one stage, you can have two stages. The first stage, you will have less pressure, and you can get some recovery. And then the second stage, you apply the full pressure here. And the area that you see here, this is what you can save. This is the energy you can save by two stages. So you go from one stage to two stages. You go from 1.56 to 1.28. No novel materials will do anything like this. In principle, if you do infinite stages, you can approach the minimum energy of desalination. I'll show you very soon. So now, this is, again, we can do the analysis, mathematical analysis of infinite stages. And then if you chemical engineers who took classes about staging operation, it's very well known. And when you do this analysis for infinite stages, we can recover exactly the equation of the Gibbs free energy of separation that I showed you earlier, which is 1.06. But we know in practicality, you will never operate in many stages. Indeed, the membrane companies know that you can reduce the energy, but we think about energy, they think about capital cost. If you have two stages, the capital cost will increase and so on. So the question now, again, I show you that we can save some energy here, but it's not advisable because they don't like to have too many physical stages. The question, can we think about some way to have something like stages but still have physically just one stage? And I would like to show you a quite innovative technology from a startup company in Israel. It's called closed circuit desalination. And here, instead of physical stages that do the separation, we will have operational stages. And the way it works, you have the feed water that enters here, and then you recirculate it and get permeate. And as you recirculate, the osmotic pressure increases, so then you need to stop and increase the pressure. You do it again, and then osmotic pressure increases, you increase the pressure, and you can do it several times, and in this way you can approach really very close to the osmotic pressure curve, which is the minimum energy, by just operational stages. You will never be able to approach the thermodynamic limit because always we have clean water that enters here and mixes. So we have mixing, which is the opposite of separation, and you lose some energy. But when you do these stages, I'll show you some example of calculations. This is compared to one stage. The one stage is the way we operate nowadays. If you have 2 operational stages, use this closed circuit desalination, do 2 operational stages, you can save 12.5%. If you do 4 stages, you can save 18.5%. And if you do the more practical one that can go all the way to 8, you can save 20%. It's dramatic saving. 20% for the desalination capacity all around the world translates to billions of dollars. So you see here, just by simple process design, we can make significant improvement on the energy of desalination. So let's see how I do with time. How do I do with time? OK. Now let's talk about what are the environmental impact of seawater desalination. So this is the 4th question. Just to remind you, a desalination plant and the interaction with the environment, we have some intake, we have some discharge to the ocean, we have some energy because of the power that you need. And let's just highlight a few of these energy concerns. One of them at the intake is the impingement and entrainment. And this is really one of the things that held the desalination plant in California for so long. When you have the intake, there is a screen, and then you can suck some organism, larvae, and many aquatic organisms. And the environmentalists were not happy about it because of affecting the aquatic organisms. And one way that California overcome it, that you will need, instead of taking the water directly from the ocean, you need to drill the intake in the dunes, and the water will go through the dunes, sand dunes, and in a way you can minimize this impingement and entrainment. Greenhouse gas emission, because it consumes a lot of energy, as I showed you, and I will show you soon some calculations. And brine discharge. Again, you start with a 35,000 ppm or 40, depends on the sea, and the brine is twice as much concentrated. You need to put it back in the ocean, and it's denser because it's higher salinity. It has some chemicals, not a lot, but some cleaning chemicals, and eventually it can affect the environment. So this is one of the concerns of environmentalists. And think about it, and again, I think Israel will need to think about it. Along the Mediterranean, at a very short range, there are 5 gigantic plants. I want to see what's the impact, 10 years from now on the Mediterranean Sea. Probably will be quite significant. So let's talk only about the aspect of the energy. And so reverse osmosis, again, the current plants, let's say rain consume between, let's say 3.5 to 5. Again, the best one, 3. Some of them 4, but some of the old one 5. Now you can calculate, again, for the kilowatt hour, and for the electricity, how much CO2 you produce for making whatever the energy that you need. So the calculation showed that you need 1.6 kilograms CO2 per cubic meter of fresh water. Let's take example, Israel. Currently, they have 0.65 billion cubic ton per year. It translates to 2,600 gigawatt hour per year, or 1 billion kilograms CO2 per year. I did just rough calculation. It's equivalent to adding over 220,000 cars, just the emission equivalent to annually for close to 250,000 cars, just to get an order of magnitude. So it's not insignificant. Now let's put everything in perspective just to show you the energy, and so you can get some idea. Just so it will help you maybe in the question, is seawater desalination sustainable or not? So again, I already told you that 3.5 kilowatt hour per cubic meter of product water, this is the current desalination plant, and the RO is 2 kilowatt hour per cubic meter. Let's compare it to California. In California, they bring the water all the way from Lake Shasta in Northern California, go to Sacramento Delta, I need to go through over the mountains pumping, and goes to the Los Angeles area. It will need, just to bring the water there before treating it, 2.3 kilowatt hour per cubic meter. So it's almost more than reverse osmosis stage. The one for the Colorado River, it's a shorter aqueduct, it's 1.6. Just an order of magnitude. Now let's go a little more. So let's see for fuel consumption. To get 1 cubic meter of water, or 1,000 liter, you need a certain electricity, which means you need to burn 0.6 kilogram oil to get this electricity. Now, what you can do with this fuel, suppose you have this fuel, to get 1,000 liters is equivalent to 2 to 9 kilometers. Can we translate to miles? Maybe 1 to 6 miles. Many of you drive to work at least 20 miles each way and so on. Just get an idea how many cubic meter or 1,000 liters of water you could have desalinated if you stopped driving. And if you think about air conditioning, again, yesterday I got to my hotel and the air conditioner was at 65 degrees, I was freezing. And just get an idea here. This fuel is equivalent to having just a single room air conditioner for 1.4 hours. In my case, probably they turn it on for the morning, I come in the evening. It's equivalent to how many? 5,000 liters of water, just to get an order of magnitude. Okay, so now I gave you answer the 4 questions, but now I'd like to go what next and mostly talk about where I think research should go and go back to the membranes and then tie together everything. Just to remind you, this is again the seawater desalination plant, and I already alluded to the fact that the post-treatment sometimes can be energy intensive because reverse osmosis membrane, although they are very good, they do not remove many things effectively, like boric acid that you have in seawater. And boric acid, or boron in short, is very important to remove because many crops are very sensitive. Indeed, the limits for boron for agriculture is lower than for human consumption, just to get an order of magnitude. Plants are much more sensitive. So just imagine, I mean, if we have membrane which really can have very high removal efficiency. So this is one thing that I would like to eventually lead to. And again, so now let's talk about the current membranes. The current reverse osmosis polyamide membrane and any membrane are what we call solution diffusion type membrane, in which the water and salt partitioning into the membrane, diffusing at different rates, and because water diffuses much faster, you achieve separation. However, these membranes are really limited by what we call the permeability selectivity trade-off. It's easy for the membrane manufacturers to remove boron. They can just tweak the membranes, and they can make the rejection very high. But when they make the rejection very high, the water permeability drops below the limit, and then you will need much more energy. And it shows here. If you have salt permeability, we need to have low salt permeability, and this is the water permeability. This data from Yip, one of my former students. You see, if we want to have higher permeability, we sacrifice by increasing the salt permeability. If we want to make very low permeability, ideally very, very low, we will have the permeability so low, so the plant will require a lot of energy. So this is really limiting us because these are the current membranes. So what we really need, there is a critical need for a new paradigm for a membrane fabrication to overcome this inherent limitation of the permeability selectivity trade-off. Now, we can present this permeability selectivity trade-off in a different way. Instead of just the salt permeability and water permeability, we adapted more from gas separation to present the water permeability over the salt permeability, which will tell you how the membrane is selective to water compared to salt. We need high value. We need a lot of selectivity for water and less salt go through as a function of water permeability. And the data that I showed you before, it's here. So the question is now, if we want to have next generation membrane, what should we do? The current membranes are roughly here. This is the membrane typically in this point of permeability and selectivity. Should we increase both water permeability and salt permeability? Should we increase only water permeability, or should we increase only the, here, A over B? It means should we increase the salt permeability so this value will increase? And we did such an analysis in a recent paper. And the conclusion of our paper, indeed, I think this is the title of the paper, the critical need for high selectivity, not high water permeability. I already showed you earlier that increasing the water permeability has minimal impact. It will not affect the desalination. Indeed, it will cause even more problem. It will cause concentration polarization, maybe will affect the salt rejection, and so on. What we suggested in this paper, and gave a lot of examples why, that we really need to focus only on increasing the salt selectivity, assuming that you will not affect the water permeability of the current membranes. I mean, so stay roughly the same range. And we discussed, and again in another recent article, what will be the next generation membrane. Again, we should have some membrane that work not based on the solution diffusion mechanism, because this solution diffusion mechanism, I mean, because of it, we have this permeability selectivity trade-off. So we discussed some membranes, and here the focus on increases selectivity. So this is where people who work, again, first time when I throw this idea, a lot of young professors that work on carbon nanotube and aquaporing were so scared, well, because water permeability will not important. But I told him, wait, we can do it also for selectivity. And I think now you just need to change the story when you write a proposal. And you can do the same thing. So anyway, we discussed aquaporing, and I will say a few words about them, and carbon nanotube, but also synthetically designed channels that you can design them in a way that will mimic some biological membranes. We discussed even some surfactants that you can polymerize and create very, very small pores, uniform size sub-nanometer. And of course, we discussed the graphene, the idea of graphene that you will have punch some holes. Again, our conclusion, I will tell you only on the thing that I think may lead to something. The two here. And again, remember, the goal here is to improve the selectivity of the membrane. It means, ideally, only water should go through and no other species. So let's talk about the aquaporin-based membrane. Aquaporin is an amazing water channel. Again, it's a unique structure with some kind of the right molecules that provide the right interactions. And some aquaporin depends, some human aquaporin or one that you can produce from bacteria. In principle, they can remove all solutes and only water will go through. It's quite amazing. So, for example, urea, which is 60 roughly gram per mole molecular weight, you can reject maybe by current reverse osmosis membrane, maybe 50% rejection. Aquaporin will have complete rejection. This is by size. But what's unique, a recent study shows some molecular dynamic simulation, and they show that some aquaporin, and again, you can show it by even experiment, and they can remove ammonia, which is the same size of water molecule, and even oxygen. And they explain it by interaction of the molecule with the functional groups in this aquaporin. And if you have more hydrophobic interaction, you can get more rejection. This is the way the rejection, even though they're relatively small, as opposed to water molecule, which is hydrophilic and go through the membrane. So in principle, if we can have these aquaporin membrane channels and put them in a membrane, it would be a dramatic improvement in seawater desalination. So there are some studies on aquaporin. Again, they started on the wrong notion that to improve water permeability, but what we think this is the way to go to improve water selectivity. And what they've done now so far in aquaporin, they just incorporated the aquaporin in vesicles, bilayers vesicles. It's easy, easy. You can do it and they will just incorporate there. And they just studied the permeability of water, and some of them study solute selectivity, very few solute, just for these vesicles. The question is now how you make it as a membrane. And this area is very challenging. And again, we are still at the stage mostly of the vesicle. Now, to get the membranes, and again, for desalination plant, you need 100,000 square meter of membranes. So you need to have a flat or planar surface. So if we can incorporate the aquaporin in a bilayer, either lipid bilayer, which is probably not the best because it will be sensitive to chemicals, pH, but if you can have this bilayer by black copolymers of layer that's hydrophobic, hydrophobic, so you can get these bilayers. And if you can find some way to incorporate the aquaporin and maintain their integrity, you can achieve in principle a membrane which, immense salt rejection. Of course, we need to have the layer, the bilayer, impermeable. We did some work and we found the most black copolymer layers are not completely impermeable, but you get selectivity which is 100 or 1,000 times more than current membrane. So very little salt go through. Another idea is carbon nanotubes. Carbon nanotubes, again, started just because of the high water flux. And when the papers published and they implied that they can be used for desalination, they did not even demonstrate salt rejection. Later studies that demonstrated 40, 30%. And I think there is a company, one of my former students, Rob McGinnis, he claimed in the recent Gordon conference for membrane about 50% salt rejection by carbon nanotube. So I would like to show you again. So the idea, if we can get carbon nanotube, and here they should be highly uniform and small in size, which is very challenging. So you need to pre-select the carbon nanotube below a certain size so you can reject all salt. And if you can find some way to align them and have a planar membrane in a scalable way, industrial way, it will be great. And I will show you some of our collaboration work with the faculty in my department, Chinido Mosuji. We find some mesophases in which you can sequester this carbon nanotube. We pre-selected this carbon nanotube so it will be uniform, because if you don't have the uniform size and some of them are over 0.8, you will have a problem. And by magnetic field, we were able to align them. And then we polymerized the matrix. And we were able to show it and so on, but we were not able to show anything going through the membrane. We're still working on it, because probably the very small carbon nanotube are probably this clogged or not open. But in my opinion, if someone will be able to align very small carbon nanotubes in a membrane, you can achieve high separation. Now, this separation can be either by size exclusion. If the pore is smaller than the solute, everything will be removed. And maybe there's some unique interaction that may mimic some of the interaction, hydrophobic interaction with the aquaporin. So I provided you a lot of information about the 4 questions. Then, again, from research point of view, where I think at least the membrane area should go. And I would like now to answer the question, is seawater desalination a sustainable solution for global water scarcity? And here I'm taking directly quotes from the review article that I've written in 2011, and we can read it together. So this is my philosophy or my opinion about it. But again, in Texas, maybe they think differently than California, and there are a lot of political issues, so there is no politics here. So we are in academia, and we cannot do it at Texas A&M. So although several options currently exist to augment freshwater sources, including treatment of low-quality local waters, water recycling and reuse. Again, wastewater reuse can be very, very important. All in all, this option alone will not be enough to meet this need in many, many places. So many places, for example, Israel is already recycling 95% of their wastewater, and still they do not have enough water. The Sea of Galilee is, again, it's just the main source. So we need to look at it in some way as an option. Then, and again, I encourage doing all other options. In my opinion, in California, they should reuse all the wastewater. And reusing wastewater, the energy that you need for reusing wastewater is 0.9 kilowatt hour per cubic meter compared to 4. And again, if you just overcome the psychological barrier of drinking recycled wastewater, again, so it will be okay. Then, while seawater desalination must be considered after all other options have been implemented, it should be viewed as a crucial component of the portfolio of water supply option. We cannot discount it as not an option. Now, before going to the last one, I just forget, when you talk about public perception of recycled wastewater, many of us drink recycled wastewater all the time. If you live along the Mississippi River, all the water, if you are in New Orleans, the water goes through the kidneys of 70 million people there. So 10% of the Mississippi is just recycled, treated wastewater. So, and lastly, for water scarce countries that already implement all other measures for freshwater generation, and I told you in Israel, they recycle 95%, practically all the wastewater. Desalination may serve as the only viable means to provide water supplies because there is no other way. And the Gulf countries like Saudi Arabia, Kuwait, Qatar, I know you have a campus in Qatar, also have desalination because they have no other water. I'm done, so I would like to thank the generation of students that I have here, and I think there are some people here. Let's see. Deborah, where are you? Deborah, let's see. Who else? I think Chile. Is this Chilean? Is this Chilean? Yeah. Where is Navid? Oh, here. Many, again, maybe I forgot, but anyway, so Navid, you look much younger now. And I would like to fund many funding agencies, and I'm part of the NUT, the Engineering Research Center, that headquartered in Rice, and I'm glad that people from NUT, like Chilean, came here. So thank you very much for your attention, and I will be able to be happy to answer any question that you have. So who wants to fill the question? You or should I?
Yeah, you can do it.
Hi. Yes. Just say your name so I will know more people.
My name is Dipesh. I'm Dr. Salih's student.
Oh, okay, good.
Thank you for the great talk. I actually have two questions.
Okay.
The first question is when you talked about the carbon nanotube enabled membrane and aligning it with a magnetic field. So I'm assuming we will have to incorporate a single wall magnetic carbon nanotubes.
No. They are diamagnetic, and again, in a way, you align the mesophases. We choose the liquid crystal, the right mesophases that are diamagnetic, and these are the ones that put the carbon nanotube. It's not the carbon nanotube itself.
Okay. And do you think it's going to be cost effective compared to what we have?
In my opinion, no. But as you know, when you do research, sometimes you need to take risk. I just cannot see how it be. We found some roll-to-roll technique that you can do it by more like scalable. But I cannot imagine it will be scalable. It's just so complicated. But who knows? Maybe some of the young scientists 10, 20 years from now. But again, you need to aspire to something. And this is, I think, one of the options. I don't know what the other senior people think, if it's scalable or not. But as you get older, you are becoming more realistic. My feeling not.
My second question is, so this is the time of crisis when we have so many refugees who are trying to migrate from Africa to Europe.
Yeah.
And they use the sea route. Sea route to
yeah.
go from here to there, and a lot of people die from dehydration. So do you think it is feasible to design something that is point of use that these guys can use when
just in the boat? It's very simple. They can buy. There's a company, Hydration Technology Innovation. It's used for osmosis. Again, it's another area of research. Forward osmosis is a semi-permeable membrane. You have it more like a bag, and inside you put more like sugar, like Gatorade type thing, which is or indeed for seawater maybe it's difficult. You're right. For seawater, I mean this one is more for surface water because you need to have a much higher osmotic pressure. For any other surface dirty water, when you put this kind of thing, you can extract water and then drink sweet water. For seawater, there are some things that you buy like a hand pump. Reverse osmosis is more like the bicycle pump that you just do by hand and you can get some water coming out.
Okay.
Yeah.
600 psi hand pump?
I don't know. I don't know if they try to seawater, but probably you need just 410. Yeah. But it's difficult. Yeah. You're right. The more it may have not been used for seawater. Yeah. But some people can remember what is 400 psi for someone like Navid or goes to the gym every day. What is 400 psi? Calculate the force, how much the Newton. I don't think it's doable, no?
Just over a small area.
Yeah, small area, okay. So it's a small area?
Yeah, they have a small piston, I think.
Yeah. Okay. You just need a few drops of water to leave. It's not that you need to. Yes, Chilin.
So you're talking about these selective membranes that many of the ideas will involve almost like a mixed matrix type of material. Mixed matrix membranes have been studied for decades and people have not been able to overcome the barrier that the interface between the two phases can never be perfect, right? Because we're talking about very small ions.
But many, again, you're right. The mixed matrix membrane, I mean, is, for those of you, mixing polymers with some inorganic materials. And I like the idea, at least for the gas separation. I think for the liquid separation, many people jump and thought that just the magic. If they throw nanomaterials to the polymer dope, there will be some magic and suddenly the permeability will increase. It's not the case. It's true when you have this mixed matrix that the boundary between the, in our case, the aquaporine and the black copolymer will be important. And this is one of the challenges. I think you can overcome it. But what I don't like in the people who jump to the mixed matrix for liquid separation, water separation, they just throw nanomaterials and zeolite that probably blocked and so on, or some nanomaterial, and they hope that just because there is the name nanomaterial, some magic will happen and the membrane will overcome the permeability selectivity trade-off. No one was able to show it so far. And the company Nano H2O do not make any nanomaterials in this membrane. It's just a name. So we will need to overcome this interface, you're right, but it's a scientific challenge. Yes?
I have a question, Meny, about the graphene work. So have you seen people using graphene oxide on membranes for desalination already? Is it marketed already?
No. It's just an idea. That, yeah.
Concept.
I mean, the concept, I think, was first just by molecular dynamic simulations, that you punch some holes, and then the Nobel laureate game suggests even something more crazier, and that you put some graphene sheets in a way, and the water will go in between, and you can achieve desalination. I don't think you can achieve very high selectivity there.
So one of the worries is that if graphene oxide starts to decay out in presence of chlorine, as have been shown already, then we might have PAHs, like membrane serving as a source of PAH.
I mean, if the membrane, you're right. First, the current membrane, you cannot use chlorine, but if the membrane will not be polyamide, people will use chlorine, and there are a lot of challenges, but again, the polyamide membrane is good, but we need to find somewhere for the young people here, some ideas for research and aspiring, and I think it's maybe doable.
Do you see reverse osmosis as the future of water treatment for seawater, or you think the other methods are also strong?
I mean, I wish there would be new technologies, but it's well accepted nowadays that reverse osmosis is the gold standard because, as I showed you, it's relatively very close to the minimum energy of desalination. So for seawater, there are some thermal technologies, but they're much more energy intensive. Unless someone finds some magic that you recover all the latent heat of condensation and reuse it with no losses, just cannot see other technologies. People suggested other, just for paper, for publishing some kind of method, but none of them will be scalable. So I still think for the years to come, RO to be, reverse osmosis to be the dominant technology.
What about the electrolysis?
Reverse osmosis is already approaching the thermodynamic limit. I just cannot see how electrodialysis will be able to do so, and how electrodialysis can remove boron, which is uncharged. And so there are a lot of issues, I mean, and high salinity. So, and electrodialysis is with us even more than reverse osmosis, and they were not able to. I think electrodialysis was developed before the first reverse osmosis. Maybe for brackish water, but I just cannot see how it can remove, and including all the new technology. Again, many of the emerging, it's called emerging technology. People do work on capacity of deionization. This technology is for 30, 40 years. People who do work on membrane distillation, it's for 30, 40 years, and it's still emerging. So which means that there is some problem there. Yes?
So it's not related to membranes.
Speak up, yeah.
It's not related to membranes. It's about the energy usage. So you mentioned the reverse osmosis process requires a lot of energy. It's very energy intensive. It leads to greenhouse emission gases. So why can't we have a reverse osmosis plant very close to the seashore and harness the tidal energy to run the plant?
Some people claim that you can try to harness energy and so on, but my point is regardless, it will need electricity. Whatever you harness the energy, you probably will feed it to the grid and then use it for the reverse osmosis. You cannot, for reverse osmosis, you cannot use fluctuating energy. So ideally, if we are now in the era that everything is solar energy, then desalination will be the best thing in the world. In a way, I was asked to review an article, a crazy article that people talk about using desalination plants, because now we worry about the rise of the ocean, to desalinate ocean water and then store it underground, all these waters, to minimize the... But any renewable energy would be great. But the forecast is that the coming even 100 years, still at least 70% will be still fossil fuel.
Another question. You mentioned about post-treatment for the desalinate water. So I would like to know what kind of research is going on for the post-treatment. I mean, what are the, what are the different processes you are looking at for post-treatment?
So when you say post-treatment, there are two things. First, have you tried once to drink deionized water? So you add some minerals, and the idea is to add some minerals, calcium, magnesium, sometimes debated, and some alkalinity and salt. So this you must do regardless. Otherwise, the water will be very corrosive. And then the other one, for using it for agriculture, you need to remove boron and chloride below a certain level. Now, not to mislead you, in Israel, they do not use the seawater, desalinated water directly to agriculture, but they use it for drinking water, which end up as wastewater. And when they recycle the wastewater, there is no desalination step, so the boron level will be very high, and it will be a problem. Yes, Shankar.
I appreciate the sentiment of your talk, but I cannot point to too many other human activities that are sustainable, including energy transmission, including the light bulbs we've been using for so many years. So would it be a better question, at least for people in the room who may, in our lifetimes, not to ask the question whether RO is the sustainable solution, or should it be the leading practical solution for the next 50 years for providing water to our growing population, both in terms of human and agricultural needs?
I wanted an attractive name in my title, but I appreciate your question, yes. So, I mean, sustainable, you know, it's everyone define it differently. Some define it quantitatively, some view it as a religion. So my focus was mostly on the environmental impact and energy, and bring you some information that you can now have the numbers and see how much you can improve, you know, and then you can do the calculation and answer. In the end, I just say what's my opinion, and I don't think there's one answer to it. So in California, I know many environmentalists. If you talk to Peter Glick and some, they will say this is the worst thing ever, and some say, oh, this is the best thing ever. So I don't think there is a clear answer here. But many other countries that if you don't have water, you will die. This is the reason I say it's open-ended. I will tell you my view, but I fed you with enough technical detail that you should be able to make your own judgment rather than jumping and seeing, like you can see news in Perth, Australia, when they build a desalination plant, we are making our ocean toxic. We cannot swim there because of all the brine and many things that you know environmentalists can scare you sometimes. So we need to be environmentally conscious, but know the technical part, and so we can really provide answers. So this was the goal of my talk. Yes, Des.
One of your early slides talked about waste of water waste in the overall use. What fraction
water waste?
Waste of water. When you were talking about how the rise is there, one of the little components was basically just waste. This is completely different from your talk, but is there space there for environmental engineers to work and to kind of reduce the need for new water supply by reducing waste? And I'm imagining that Israel is a leader in that. So.
Yeah, I think to transfer the question of this, I showed some diagram of the increase in water consumption, but if you look carefully, and he was able to see, one of them was water withdrawals, and one of them is water consumption, so the difference is the waste. And I think I alluded to it in my final slide, that any low marginal water, if you can use them and recycle them with less energy than seawater, you should go through them, and then use desalination as a last resort. So the answer is yes, if you can do it, it would be great.
Without having done the numbers, my sense is that there's a big space there.
Yeah. I mean, all the waste. I mean, even just on the big city, how much the water that they are losing just for leaking pipes is 30% in big city. So it's amazing. So this is what I said, desalination. If you solve all the other problems, there will be much, much less energy intensive, and use it as a last resort. Now, what's intriguing about desalination, and I go a lot to visit China, Korea, all these places, many countries reach a point that they want to have desalination plant as a proof that they are technologically savvy. It's more like having a nuclear capability. And many times you don't need it. I mean, you can do it by other ways. So it's more like, we are proud, we can have a desalination plant. So, yes, Charlie.
I was wondering on the reject, when you look at all the salt and the boron and everything else that you're accumulating, are there growing issues with that, or kind of growing issues, environmental impacts, or concerns, or new ways to manage that are kind of innovative, or is that should that be an area of growing concern?
When you talk about seawater desalination, the easiest way and the cheapest way is just to put it in the ocean. And if you do it the right way, far away from and places there is mixing and the right diffuser, I don't think it can be a major problem in terms of the trace concentration that you have there. In inland desalination plant, when you desalinate brackish water, it's a major issue what to do with the brine. And when you do deep well injection, you heard about the earthquake in Oklahoma, it was because of deep well injection. So it's a major problem. Some other research think about zero liquid discharge, when you concentrate everything and recover the elements, but you'll be so energy intensive because the energy of desalination proportional to the salt concentration. As you concentrate more, you'll be so energy intensive. So my feeling for the ocean, as long as you don't build, a crazy number of desalination plants, it can be done. Yes?
Question. So I was actually at a talk yesterday about also desalination's potential pathway.
Where?
So I'm currently under a professor at the Department of Chemical Engineering doing research on localized solutions, specifically for Houston.
Okay.
What would you say, instead of using reverse osmosis as a generic term that everyone should look for a better membrane and we should all do reverse osmosis, would you say looking for a more localized solution per the area you're in would be a better solution to solve the water need, the water problem?
When you say localized solution that involves desalination?
Yes. For example, like our research is looking into using waste energy and waste heat from refineries to pump a, I guess you could say, high vapor compression desalination system instead of per se pumping electricity into it.
But how do you drive it with the waste heat?
And so the waste heat is working through a heat exchanger to heat the desalinated water and then take the steam and use that as part of it.
Okay. You know, there are a lot of solutions. We did also some research on some technologies like reverse osmosis that use low-grade heat. But here I focus on large-scale desalination plant. There is not a lot of waste heat as most people think. Not a lot. It's just for very small things, yeah, you can do it. But I was focusing more on the large mega desalination plants. And I cannot see any other incorporating waste heat there in such a way. Now, some people think about you can have some thermal waste heat, and many times, if it's more efficient to produce electricity from the waste heat, it's better to produce electricity and use reverse osmosis, because if you use it for thermal desalination, the thermal desalination is not inherently is not efficient. Chilin, you're asking your advisor too much questions, too many questions.
As you pointed out, reuse of wastewater is perhaps a much more reasonable solution.
Energy-wise.
Yeah, especially at large scale, municipality scale.
Yeah.
And right now, the golden standard is still reverse osmosis.
Yes.
But if you compare reverse osmosis with nanofiltration, the required pressure is much lower for nanofiltration. The salt concentration in municipal wastewater is not very high.
Yeah, okay.
You probably don't need the 95% or 99% salt rejection, right?
So,
So wouldn't a better solution be you can tailor nanofiltration membranes so you can get good rejection of whatever contaminants that are in wastewater, but maintain a low salt rejection so you can minimize energy consumption at small scale?
I mean, for wastewater reuse, the energy is already low. And although they use reverse osmosis, they use low pressure brackish reverse osmosis. I can call it a tight nanofiltration membrane. I don't think you want to have it too open, then all the PCP, personal care product, pharmaceutical, you don't want everything to go through. Then you need to have much more intense advanced oxidation at the end. Because, in my opinion, because the energy is already not as high, so if you have nanofiltration, you may drop it to from 0.9 to 0.7, but then you have all these things that you need to take care of because pharmaceuticals will go through and so on. But again, they are not using high rejection membranes there. They're using brackish water RO. It's my opinion, yeah. Because when energy is too low, so you don't need to be bothered too much. I'm talking about the 4 kilowatt hour per cubic meter compared to 0.9. It's a huge difference.
We have time for one last question.
Ooh, a lot of pressure. Better be a good one.
Many days, sir.
Okay.
Are there any successful examples of reverse osmosis plants in the developing world?
Depends how you define developing world. You know, when I was in China, they insisted to call China, the people that are administration, they are brainwashed, they developing countries. In China, they are. But the real developing country, I've not seen any desalination plants. But again, it's when you said developing countries, depends what your definition. Is it emerging economy, poor country? In sub-Saharan Africa, you will not see desalination plant, of course not. It's just too energy intensive and too sophisticated for that place.
Yeah, with that, couple of announcements. Please, the faculty, please come down so that we can take a picture. And after the